We will now find the derivative of inverse sine of x using implicit differentiation. Here's how it works. Suppose we want to find the derivative dy dx of y equals inverse sine of x. Currently, we don't know anything about inverse sine of x, but we do know a whole lot about sine of x. So let's flip this. If y equals inverse sine of x, then sine of y must equal x. Now let's use implicit differentiation. We have that d dx of sine of y must equal d dx of x. On the right, we get 1. On the left, we get the derivative of sine of y, which is cosine of y times dy dx because y is a function of x. Solving for dy dx, we get that dy dx must equal 1 over cosine of y. We started with an explicit function in terms of x, so we'd like to end in terms of x too. So let's use what we know about y. We know that sine of y equals x. Back in pre-calc, we learned that this means that there must be a relationship between x and y in terms of the unit circle. If we build a triangle with hypotenuse 1 with angle y, then the SO in SOHCAHTOA says that sine of y must equal the opposite over hypotenuse. But we know that the hypotenuse is 1, and that sine of y equals x, so x must be the opposite part. So we put that on our triangle. If we want to represent cosine of y in a different way, we can use the CA in SOHCAHTOA so that cosine of y equals adjacent over hypotenuse. The hypotenuse is still 1, and the adjacent part we can solve for using the Pythagorean theorem. It will be the square root of 1 minus x squared. This means that cosine of y equals square root of 1 minus x squared. Replacing that in the derivative, we get that the derivative of inverse sine of x is 1 divided by square root of 1 minus x squared. Notice that this only makes sense when x is between minus 1 and 1, but that's okay. Let's look at the graph of arcsine again. It would only make sense to put tangent lines on the values of x between minus 1 and 1 because that's where it's defined, and at endpoints we can't make a well-defined tangent line, so we're good. Arc cosine of x and arc tangent of x have similar explanations, which I'll leave to the listener. I'll list them here. Notice that, just like with cosine of x, arc cosine of x has a negative sign in its derivative. Also notice that arc tangent of x is defined for all real numbers. Let's do a quick example. Find dy dx for y equals arcsine of the square root of 3x. We have to use the chain rule for this. Our outside function is arcsine and the inside is square root of 3x. So then we proceed. The derivative will be 1 over the square root of 1 minus square root of 3x quantity squared times the derivative of square root of 3x, which is 1/2 times the quantity 3x raised to the minus 1/2 times 3. Notice that I multiply by 3 because I'm taking the derivative of 3x. This is a commonly missed step when taking this derivative, so always make sure to double check your work. Let's quickly observe the domain of this derivative function. Since we need positive numbers inside the square roots, x must be greater than 0. Inside the bigger square root function, we need that the square root of 3x is smaller than 1, so 3x must be greater than 0 and less than 1, so the domain is x between 0 and 1/3. There are also derivatives of the inverse trig functions for cosecant, secant, and cotangent, which I've listed here. These are not necessary to memorize at this point, but you should be familiar enough with them to recognize them.